Hello, everybody. Usually, the further we go into analyzing a subject, the more that we gather data, the more we analyze that data. Usually, we see a lot of nuances. In this case, the opposite is going to happen looking at four very different sports. In fact, things will become more similar. We're looking at the remarkable similarity of the female versus male velocity ratio of Olympic champions in four sports: swimming, rowing, speed skating, and running, two aquatic and one on land. Well, let's look fundamentally at differences. Now, we can't see how much energy is stored in the muscles due to training. I'm looking at the overall changes or lack of those. There's not much difference in physique. Now, there's an 80-year difference at 100 meters. Physique is about the same. Swimsuits are the same. But instead of starting at the edge of the pool, the starting block is way up here. Swimmers now have lane markers to block waves, and the goggles allow them to swim without damaging their eyes. I was a swimmer for 7 years, and I was bloodshot for 7 years. This really limited the amount of time I could swim. Today's swimmers are 26% faster over those 80 years. In rowing, over 80 years at single sculls, by the way, the other event was 100 meters, we really see little difference in anything regarding the nature of the sport or the physique. But if we look really carefully, Ulf Tifta has a bit more definition in his biceps. We see his quadriceps. He did not get that rowing in Norway in the winter. I've been to Norway summer and winter. I like summer. That's when the sun's out. What he did get it at, though, was we developed rowing machines. So Olaf, compared to Jack Beresford, he can train anytime he wanted to, and that explains why he was the Olympic champion, 13% faster than 80 years before. We moved to 82-year difference in men's 500 meters speed skating. These two look like twin brothers. The ice conditions are far better. We have lightweight, dry, waterproof suits compared to this. And where Jutra is leaning forward, he had to lift the skate to keep from tripping. Cheek can have his clap skate in contact with the ice the whole time. 21 second difference. Fundamentally, though, the stroke, the motion of the skater, forward leg, back leg, basically the same. So we can analyze with the same technology. Running. Notice that the track conditions are far better, no slippery track, much better shoes, much lighter weight, form-fitting uniform. Fundamentally, though, the physiology is not that much different. Certainly the stroke, the forward motion of the leg and the forward leg and back leg haven't changed over the 80 years, but they're 12% faster today for a combination of reasons. But fundamentally, the sports are the same. Notice the back kick here is the same as it was 80 years earlier. Okay, we have four very different sports. The photos show that technology has improved performance in the four very different sports. To understand the velocity ratio of female versus male Olympic champions, I'm going to use kinesiology and physics to build a model for each sport. Surprisingly, the models will be almost exactly the same the deeper we go. The actual theoretical ratios will then be compared to the actual value of the ratio of Olympic champions. Well, let's start with swimming and rowing. What you have to do is apply the power to push against water. Well, and in each case, but the equations aren't quite the same. Now we have lean body mass training and efficiency, of course. But for rowing, there is a cranking term, as I call it, required because the whole body pulls and cranks the oars. That's not true in swimming, but in swimming, analyses in flumes of moving water show that there's a propeller efficiency in that swimmers, the larger swimmers, are more efficient. So the equations aren't the same. The water pulls back, and that gives us velocity equalizing the forward force, forward power. Well, we have the cube of velocity, this total surface area that's in contact, could be in contact with the water, times the drag coefficient that gives us the actual amount in contact with the water. They look alike, but there's a big difference in rowing. The drag characteristics of all racing shells are totally controlled. So men and women will have the same drag coefficient for the racing shell, which will cancel out, but that will not happen in swimming. So now we solve for velocity. We have lean to weight rate, relative lean to weight ratio, but in rowing you multiply by the cranking ratio. In swimming you divide by the drag ratio, the drag telling us, drag coefficient, how much of the body mass is actually affected by water. The ratio of mass, body mass, has different powers. Well, all right, the next thing I did was I found studies, reliable studies involving nearly 2,300 athletes. And there are some results that make perfect sense right after we know them. That happens a lot. The lean to weight ratio is the same as the relative cranking, because the higher is your lean to weight ratio, that means how much power your body can put out, the higher will be your effort at cranking. For swimming, the relative lean to weight is the same as the relative drag coefficient, all right? The relative lean to weight is a measure of body density. The less dense you have, the higher the swimmer, women, for example, are in the water. And by being higher in the water, they are in less contact with less water, and the drag ratio is lower, and vice versa for a greater density. Okay, those make sense. The one that is harder to explain is that the square of lean to weight is body mass. I've seen this in other contexts. When athletes are trying to increase their lean to weight ratio by training, first you drop body fat, then gain body mass. The before and after ratios show this ratio. The square of the change in lean to weight is equal body mass weight ratio change. Here we're looking at, it makes sense, probably because of metabolism, that this is true for a cross section of swimmers and rowers. So what happens when I substitute? Now, when I have approximately here, I mean within tenths of a percent. I don't mean close. I mean almost exactly the same. I substitute those in and we get the same result. The deeper we went, the closer they became. Here we have the 8/9 ratio of lean to weight, and we have training efficiency. If training and efficiency are the same, then the 8/9 ratio of lean to weight would give us the velocity ratio. Well, okay, now let's move to running and speed skating. We apply power against the ground. Gravity pulls back to create a balance. The equations are exactly the same. Power times efficiency gives us the effect of gravity. Now there's angles involved, which I'm not showing. They are different between the sports, but for men and women in each sport, they're about the same and cancel out. So when we solve for velocity ratio, it depends on the lean to weight, training, and efficiency. Surprisingly, when I put them both together, they come out almost exactly the same. Now, the two aquatic sports have the 8/9 power of lean to weight. The two gravity-based sports have the 9/9, you could say, first power of lean to weight. Although the power of training and efficiency is not the same, if women and men are equally trained and efficient, these very similar equations are all we need. All right, so much for theory. What really happens? I divided the Olympic history into 5 periods. World War I in recovery, World War II in recovery, the Cold War era, The boycotts and recovery from 80 to 88, and what I call the anti-drug period from 92 to now, 2018, in Winter Olympics. The left-hand side of each sport is what we would estimate from physiology, assuming equal training and efficiency. The right size is what we actually have for the Olympic champions. In swimming, the Olympic champions gained and gained and gained for women relative to men, as happened in rowing. Now, rowing has only been 2,000 meters recently. And then the difference, we had equal training and efficiency, so not much change anymore. Here's the interesting part. We expect 90% velocity ratio from physiology with equal training and efficiency. We get a 90% ratio of Olympic champions. Okay, then we get good verification of our equations. We move to running and speed skating. In running, women have gained relative to men. In speed skating, women gain relative to men. And now we expect equal training and efficiency. But let's look at the data from 80 to 88. We expect a 92% velocity ratio based on physiology for equal training and efficiency. We do get a 92% relationship in speed skating, but 91% in running. In more recent times, we expect a 91% velocity ratio of Olympic champions. We get 90. There's a change, there's a loss of 1%. Where is that coming from? I do not think it's a problem of training, or we would have seen that in the other sports. I do think it's an efficiency. Women have 6 times the likelihood of ACL tears compared to men. Women's hips are wider relative to their height than men, causing women to overstride relative to men. I believe that overstriding is where the 1% loss of efficiency is due to. We don't want women to stride in a way that is not fit their body geometry. Female athletes should strengthen their knees to reduce the likelihood of an ACL tear. And in my 2 trips to the Olympic Training Center in Colorado Springs, I see women doing just that. The trainers make sure they've strengthened the knees. So in summary, the theoretical female over male velocity ratio for elite athletes is essentially the same for the 4 sports, but the actual velocity ratio for Olympic champions follows the lean to weight ratio, indicating equal training and efficiency, except for running, where I believe women have an inefficiency due to overstriding based on body geometry. What makes sports fun is the irrepressible nature of Olympic athletes. Jessica Ennis in the pentathlon and Jesse Owens in track. I met Jesse Owens. He wanted to talk to us at a swimming meet I was involved in when I was in high school. My white high school was swimming a black high school. Neither of us had a pool. That sort of level of equality, racial inequality, got his attention. We were put in a small school pool in the downtown, and we did not know he was coming. He wanted to tell us there's nothing you can do about what people think about you or what people say about you. There is one thing you can always do. You can always do your best. That was Jesse Owens. He always did his best in spite of all the prejudice against him. And that works today as well as it does then. The naysayers lose if you do your best. And that's all you can do is do your best. So I leave you with those wonderful words of the greatest athlete, in my opinion, Jesse Owens, a great man. And I wish you all well. Stay healthy, everyone.